And then we looked at this very interesting New York City Kaggle competition. It was a very, very interesting competition. And what I'll do is we'll try to go over some of the ideas that are present in this particular problem statement. And it's a very real world use case where the different cab aggregators that we have, like Uber, Lyft, if you're in places like Singapore, Malaysia, you will use something called Grab. If you're in let's say other parts of the world, you have other applications that are there, right? So the idea is, if you're in India, we have Ola, Uber, obviously. So here, if you see, based on the different attributes of the ride, we are trying to predict what is the price of the ride. Again, it's a very, very real world machine learning regression problem that we are trying to solve. And if you look at the data set, every row corresponds to a particular ride. So we have the fare amount. What is the fare for the ride? The pickup date, the pickup latitude, longitude, the drop off latitude, longitude, and the passenger count. So this is my data set. You can ignore the key. The key column is an identity kind of column, so you can ignore that. But everything else apart from that are part of my features, X's. Okay. And what is the Y? The output is fare amount. Okay, so that is the X and the Y combination. So whenever you're framing, whenever you're trying to solve any regression problem, the initial phase is very, very important when you're trying to frame the problem. You need to be very clear what is your X and what is your Y. So this is my X. So whenever a person is booking the ride, they will enter all these parameters, right? Isn't it? So when you're opening up the application, you have a pickup time. Latitude, longitude is where your source location is, where you're starting from. Drop off is where you want to go. You will enter these parameters. You will enter how many people you want to travel with. Like these are also important. Like if you're going to, like in certain applications, they ask you to enter how many passengers will travel. So depending on that, the pricing will also be adjusted. Okay, in US and all this is very common. You have to enter the passenger count also. So based on these features, the model will predict what is the fare count. So the fare count is what we want to effectively predict. Okay. Now, this is again a standard, a very simple problem. So what is the key takeaway from this exercise? The key takeaway is we are trying to learn a lot of different types of feature engineering techniques, right? We are using a slightly different technical term right now, feature engineering. This is actually a very, very good use case for feature engineering. So feature engineering is the idea where we try to use a set of features. Okay, it is the idea where we try to use a set of features, and based on that, we try to predict. We try to, kind of generate new features. So based on a certain initial set of features, we are trying to create new features. That is what we do as part of feature engineering. And why is it important? Why is it important particularly for this exercise? Because if you look at it, friends, if you look at the initial set of features we have, the initial set of features are not good. These are not good quality features. I mean, if you see latitude, longitude is not a good quality feature. This is not a good predictor of fare. If I want to predict the fare of a ride, latitude, longitude are numerical variables, right? These are useless variables. This is not a good predictor of fare. This is the same conversation I was having a while back. I told you that, okay, identity columns are bad features. They don't have any predictive information about the output. So similarly, latitude, longitude per se are bad quality features. What will be interesting to get from here? Maybe from latitude, longitude, I want to find out the place, the location of the ride. So if you're booking a ride in Bangalore, you want to travel from HSR layout to Koramangala, that is what is important. We want to look at the localities because the pricing will be dependent on the localities. Okay, so right now, let's say the heavy rains are happening, and if you're booking a ride from place A to place B, these kinds of models are getting used. The numbers are not important, like -73, +40 is not important. What is important is, can I map this latitude, longitude, and can I narrow down and say, hey, this, this is HSR layout. So the passenger is booking a ride from HSR to Koramangala. These are the features of the ride. You will one-hot encode these features, and now you try to predict the fare. That's the thing. Okay, so we'll go over that, but we'll see all those techniques right now. And the very, very interesting part of the exercise is we will see what are the different types of feature engineering things that we can go back and do here, right? So let's see. So first iteration one, what we do is we build a baseline model with the raw features. This is again a very, very common approach that we follow. So whenever we face with a difficult problem, there are a lot of things that we can potentially do. But one of the very first things that we should try to do is we should always try to build a baseline model. Okay, so this is one of the first things that we should try to do. We should always try to go and build a baseline model. So take the data as it is and try to build a baseline model with the raw features. So that's the first and foremost thing that we will try to do. So we'll try to take the data as it is, and based on that, we will try to build a baseline model. So build a baseline model using the raw features. So take the X and Y and build a baseline model. So we are getting something like 73%. So 73% is the R squared we are getting for the baseline model. So can we do better than this? Okay, because I told you machine learning is a process where you're constantly trying to become better. It's a very exploratory process. We never know what will work, what will not work. So we are constantly going to try out different techniques now. So we'll try to add some features, remove some outliers. We'll try out different models, and we'll see which model is giving us the best performance. So this is kind of a very exploratory way how we will, approach this particular thing here. Okay, so now what we are doing is now we are removing outliers because there are a lot of outliers in the data. If you see fair amount, if we see the distribution of our data, we'll see that most of the fares are around $0 to $20 because most of the rides are normal rides. So the fares are all between $0 to $50. Most of the fares are here, and very interesting. There are some fares which are negative, and also there are some fares which are $1,200. Like this is very hard to believe. Like fare of a cab ride is $1,200, and that too this is within NYC. So within NYC, if you're traveling from some place to another place, like $1,200 is like that's a lot of money. That's huge. That's huge. I mean, it's hard to believe that within NYC, if you're traveling, the fare can be this high. So most likely this could be some outstation ride, or maybe the GPS coordinates were not picked up correctly, or there were some errors in the application, and we will want to remove this kind of data. Because remember, if you have outliers, and if those outliers do not make sense, right? As I told you, like some extreme values with really high fare and negative fares, like maybe they are potential outliers. We don't know. We don't know. They are potential outliers. And if you look at this in detail, if you look at the another thing, if you look at the latitude, longitude of the bookings, you will see very interesting. Most of the rides happened here, but there are some outliers. This is the latitude, longitude of New York City, right? But you will see that there are some rides. There are some rides that happened beyond these coordinates. So there were some rides that were booked away from New York City. So most likely there were some GPS errors. Oftentimes it happens, like because GPS depends on your mobile phone, right? So it can happen that you're booking a cab, but the GPS is not picked up correctly. So maybe the source is taken to be something else, and the destination is taken to be something else. It's very normal, very common. Sometimes it might happen. It might happen that the GPS coordinates are not picked up correctly, right? So now we try to build another baseline model after removing the outliers. So now you remove the outliers and you try to build another baseline model, and these are the scores you're getting, 76%. So can you see the small improvement that we got? So iteration one, we got 73%. Okay, so this was the baseline model that we built initially. We got 73% accuracy. And iteration two, we removed the outliers and we built a model. And now we are getting 76% accuracy. Okay, so when we remove the outliers and now we build another model, and now we are getting 76% accuracy. So that is the R squared we are getting now. Small improvement. See how small improvements we are making. Iteration number three, experiment number three. Now what we will try to do, we have a date time feature, friends. Okay? Remember, we have a date time feature. So date time is not a useful column. Okay, so if you want to predict the fare of a ride, let me take you back to the original data. If you want to predict your fare, this is not a good predictor of fare. So if I just try to take this as X and try to predict this Y, you will not see a good relationship because this is a date time format, right? This is useless. You will not find any correlation. So you have to convert this data. So from the date time column, we can try to find out temporal features. What are temporal features? We can try to find out features like, hey, what is the hour of the ride? Okay, what is the time of the ride? Something of that sort. So these are the kind of features we can try to decipher. Okay, so from the original date time feature, we can try to extract temporal features. Year, month, day, hour, day of week. Now, the whole idea is once you end up creating these features, you can see we have created all these 4-5 features here. Now we can remove the date time feature and say that, hey, keeping every other factor constant, this is a good predictor of the output. So, I mean, you can say the day of the week is a good predictor of the fare, which is expected, right? See, Monday to Friday, these are the weekdays, right? So typically the fares will be high. Given every other factor is constant, even if you look at rush hour 9 o'clock traffic, Monday to Friday, 9 o'clock bookings, the fares will be high. Saturday, Sunday, 9 o'clock bookings, the fares will be low. So keeping every other factor constant, the day of the week is a good predictor of fare. If you tell me what day of the week it is, I can predict that whether the fare will be high or low. This is a good feature. The hour of the day is again a good predictor of the output. If you look at the hour of the day, typically again, it's very obvious, right? So if you look at anywhere, I think the rush hour usually starts from 8 o'clock. 8 o'clock very easily is the rush hour. So 8 o'clock to night 8. Morning 8 to evening 8 is rush hour. Right? Generally, it can be different for different parts of the world. I mean, if you look at India, 8 to 8 is very normal. If you look at Middle East, then I think it's work starts very early here. It's 6 o'clock, so 6 to afternoon is very normal. So peak hours are different, but then the idea is that 8 to 8 is right. Like keep every other factor constant. The hour is a good predictor of fare. Okay, if you're trying to book a cab at 2 o'clock at night, the fares will be low. Even if you're booking a ride from HSR to Bangalore airport, you will see that if you're booking at night, middle of the night, the fares will be very, very low generally. Okay, so now moving on with these features, we are building the model and we see 77.5% R squared. See how we are making small incremental improvements in the overall performance. This is the way how we actually build machine learning models in the real world. Okay, because our data will be very difficult, so we will always experiment. We will never know what will really work. We will try out, we will try adding features, try removing outliers, try different permutation combinations, and try to improve the model. So that's why we say that in machine learning projects, typically getting a POC ready is very easy. It's very easy to take some data, take some sample data, use Python, use the sklearn frameworks. You can very easily create a proof of concept. That is very easy. There's nothing. In fact, after we complete these discussions, everybody should be able to, have a working proof of concept, in a matter of like what hours. Shouldn't take much time. Okay, with all the generated tools that we have. But what will take time is doing this. This is the part that will take time. And oftentimes, this is the part that your tools will not help you. You need to brainstorm. You need to figure out, okay, based on my domain, what I think are important. See, like for example, adding trip distance as a feature. I remember I told you latitude, longitude are the original columns I had, but they are useless. But from latitude, longitude, what I can do, I can now try to add another feature called distance. Distance will be a very good feature. I mean, keeping every other factor constant, distance is a very good predictor of the fare. So it's obvious, right? If you travel more distance, you will pay more fare. If you travel less distance, you will pay less fare. It's very obvious. And the moment I include that, my R squared has shot up to 83%. So see the process we are following right now. So we are using domain knowledge. We are making a hypothesis that hey, I think this will work. I think this will work. You're using your domain knowledge. You think that okay, based on the cab data set, I think that distance is a good predictor of fare. You have a hypothesis. Then you build a model and you try to test the hypothesis. That's the way how we are going about it. Okay, so this is the general process we will follow. So you have a hypothesis, you think this is a good predictor of fare, and then you are actually using you're actually building a model to test your hypothesis. And indeed, you're getting 83% accuracy. So indeed, our hypothesis is true. So it's a good quality feature. So we have made an incremental improvement in the overall model quality. So the same way we are trying the other features, we are adding a feature for airport trips. You can see that here we have added a set of 6 features for airport pickup and drops. So there are 3 airports in and around the vicinity of NYC, New York City. So John F. Kennedy International Airport. Is it a pickup ride from JFK? Is it a drop-off ride to JFK? Is it a pickup ride from Newark Airport? Is it a drop-off ride to Newark Airport? Newark, Newark, Newark. And is it a pickup ride from LaGuardia, or is it a drop-off ride to LaGuardia? And again, if you think about it, this is important because again, keeping every other factor constant, if I know it is an airport ride, the fares will be high. And if I know it is not an airport ride, the fares will be low. So knowing whether it is an airport ride or not an airport ride is also a very, very important characteristic. So we are using that and building the model. It's a very, very small improvement that we are getting. 83.1% accuracy we are getting right now. So this is the information that we are getting right now. Next up, we are trying with long and short trips as a feature. So we are adding a calculated feature for long and short trips. So we are looking at the distance and trying to classify whether it is a long trip or whether it is not a long trip. So this is the classification that we are trying to do. Okay, so based on the features, is it a long trip? Yes. Is it not a long trip? No. So by adding this once again, we have made a small incremental improvement in the quality of the model. So this is all the different techniques we are trying out. And by doing all of that, by fine tuning, by adjusting the hyperparameters, we have finally got a model which is 86.5% accuracy or R squared. Okay, so this is the key takeaway from the exercise where it's a wonderful application of feature engineering, where we start off with a data set with absolute raw features like latitude, longitude, time, like how the real world data will look like, and how from that completely raw data set we have managed to apply different types of domain-based feature engineering techniques, and we are able to build a much better quality model. We've created better quality features. We created features like distance and all that. And by doing that, we have managed to create a much better quality model. So which is giving us a score close to 86.5%. Okay. So all of you can see that.